Weak acids ionize only slightly in solution. Acetic acid is a weak acid. It's not one of these 6 strong acids. When you put acetic acid into water, it forms hydronium and acetates. We can write a K expression for this reaction. K is equal to products multiplied together divided by reactants. And I'm going to leave out water because water is a liquid and the concentrations of liquids do not change. We're going to give this a slightly different name. We're going to call it Ka, where A indicates that acetic acid is an acid, and Ka is an ionization constant. So let's go through a problem where we solve for the ionization constant Ka. We're given acetic acid solution, we're given the concentration 0.1, and we're given the pH. pH is equal to negative log of hydronium. And so if I know the pH, 2.88, I can find hydronium by taking the antilog of negative 2.88. Hydronium comes out to 0.00132 molar. Now I need an equation. Acetic acid reacts with water. Acids always produce H3O. And acids lose a hydrogen, so we get acetate ion. Then we're going to do icebox, initial, change, equilibrium. Initially, 0.1 for the acetic acid. Water we don't worry about. Products are 0. I also know at equilibrium, H3O is 0.00132. So therefore, I know the change for H3O is 0.00132. Now the coefficients are 1 to 1 to 1. So if I know the change for one species, I know the change for all species. Products, we add that 0.00132. So at equilibrium, both products are the same. For the reactants, we subtract 0.00132. So at equilibrium, acetic acid 0.09868 molar. Now these are the concentrations that we use when we solve for Ka. So here's how we solve for Ka. Ka is equal to products. Go back to my equation, H3O times acetate divided by acetic acid. Plug in our equilibrium concentrations. And we'll get the value for Ka, which is the ionization constant for acetic acid. So Ka for acetic acid, 1.7, 10 to the negative 5. And it has no units associated with it. So we found Ka. Now let's look at a problem where we're solving for the concentrations of all species present in a solution of acetic acid. So we need the same equation. Acetic acid reacts with water. We always need an equation for a weak acid or a weak base. And we're going to do icebox. Initially is 0.5 molar. Products are 0. We don't know any of the equilibrium concentrations, so we're going to have to use a variable. We'll use x. So products are plus x. And reactants are minus x. And then we're going to set up a Ka expression. Ka we just found for acetic acid, 1.7 times 10 to the negative 5. And that's equal to products, which is x times x, divided by 0.5 minus x. So there is our Ka expression. Now let's go back and simplify that. So let's simplify the Ka expression. When we simplify it, it looks like this. X squared plus 1.7 10 to the negative 5x minus 8.5 10 to the negative 6 equals 0. So when I simplify the Ka, it comes out to a quadratic. Well, the quadratic is x equal to negative b plus or minus square root b squared minus 4ac divided by 2a. And I will assume that you know how to solve the quadratic. You're going to get two answers. Only one is going to work for us. And that value comes out to 0.0029. So x is equal to the concentration of H3O plus at equilibrium, which is the same as acetate, and that's 0.0029 molar. Acetic acid is equal to 0.5 minus x, which for all practical purposes comes out to 0.5 when we go to sig figs. So the concentration of acetic acid doesn't really change. So we have the concentrations of hydronium, acetate, and acetic acid. There's one more species present. Anytime you have H3O, you also have OH, and vice versa, because OH comes from the dissociation of water. So if I take 10 to the negative 14th and I divide by x, I get the concentration of OH. It's very small, but it's still present. 3.4 10 to the negative 12th molar. So those are the four species that are present in a solution of acetic acid. Now, we can avoid the use of the quadratic equation if we assume x is negligible compared to 0.5. So our Ka expression was 1.7 10 to the negative 5 equals x squared over 0.5 minus x. If I assume x is negligible compared to 0.5, I can get rid of minus x. And I can avoid the quadratic altogether. If I solve this equation right here for x, x comes out to 0.0029. Comes out to the same value. As a rule of thumb, we can assume x is negligible if your Ka is 10 to the negative 5th or less. Well, ours was 1.7 times 10 to the negative 5th. And the concentration of the acid or base is 0.01 or greater. And for us, it was 0.5. So if you want to avoid the quadratic, just make sure those two criteria are met, and we can get rid of minus x. When a weak base ionizes, it picks up a hydrogen ion. So NH3, for example, is a weak base, and when you put a weak base in water, it picks up a hydrogen, so you get NH4 plus, and bases always form hydroxide, OH minus. And we can write a Kb expression this time where B indicates we have a weak base. So let's look at an example with a weak base problem. We have ammonia. We need an equation, NH3 plus water. Bases pick up a hydrogen, so NH3 becomes NH4 plus, and bases always form hydroxide. Do an icebox. Initially, NH3 is 0.2. Products are 0. We don't know any of the other variables, so we'll have to use x's. Set up a Kb expression. Kb for ammonia is 1.7 times 10 to the negative 5th. On the previous slide, I gave you that value. So there's my Kb. That's going to be equal to x squared divided by 0.2 minus x. But we can assume x is negligible because my K value is 10 to the negative 5th, and I'm starting with 0.2. So I can avoid the quadratic. I can solve for x this way. X is equal to the concentration of, we go back to my equation, OH minus. And that comes out to 0.0018 molar. So there's one part of the problem. Calculate the concentration of OH minus. I also need the pH. Well, if I know OH, I can find POH, which is negative log of 0.0018. And the POH comes out to 2.74. So if I want the pH, I simply take 14 minus 2.74. pH comes out to 11.26. So that's basic, and we would expect it to be basic because it's a weak base. Percent ionization. Percent ionization is how much of this weak base ionized. We're going to take X, which is how much ionized, so 0.0018, divide by the initial, which is 0.2 for this weak base, multiply by 100. So the percent ionization, it's actually very small, 0.9%. So only 0.9% of the NH3 ionized. Strong bases ionize completely, 100%. Weak bases ionize only slightly, in this case, 0.9%.